So I'm going to talk about embedded processors. We're going to provide a brief view of the processors used in cyber physical systems, embedded systems. We're going to talk about a few different types of processors. And at the end, we're going to talk about parallelism that's supported by the processors. So first, how do we view of different processors? Of course, you can say this processor is from vendor A, that processor is from vendor B. But overall, these processors from different vendors, they may share common characteristics. And one of the major characteristics is the instruction set architecture. Instruction set architecture, or ISA in short, is a abstraction of the processor or abstraction of the machine as seen by the programmer. Another way to understand this is ISA defines the assembly level instructions that a programmer may use in their assembly language programs. So essentially, it defines what kind of registers are there for the programmers to use and how we should write instructions and to operate on these registers and also memory locations. So it's very common that you have a few different vendors, their processors use the same instruction set. I'll give you an example. So x86 is one of the most popular instruction set, not necessarily in embedded systems, but in the computing domain in general. You can find these processors, these instruction sets in processors that are used in your laptop, your desktop, or data center servers. And they may from different vendors. And two major vendors are Intel and AMD. Both of them produce processors that support x86 instruction set. As a result, if you write an assembly language program, chances are you can use this same program to run on an Intel processor and later on an AMD processor because they share the same instruction set. So for programmer, they only have to know one instruction set if the program knows that the design will eventually use this type of processors with this particular instruction set architecture. To give you another example, for Arduino platforms, these boards, they have different models of these boards or variants of these boards. We are using the Mega 2560. And last time I showed you a design that used a smaller Arduino board, the Arduino Uno. And these two boards, they use the same, they actually use different processors, slightly different processors. But these two processors following the same instruction set, this AVR instruction set. So the programs that you write, if you write in assembly language, chances are you can run the program, majority of the program, on a different AVR processor. Okay, so that was about the instruction set architecture. The next view is the microarchitecture. Microarchitecture is not to be seen or visible or used by the programmers. It's more about in the chip design, when the vendor design and manufacture this chip, what kind of physical realization of the ISA takes place underneath the instruction set. So the microarchitecture defines, for example, do you use out-of-order execution? Do you do branch prediction? These type of things that's more related to performance improvement of a particular design or power consumption optimization, but it will not change the instruction set architecture. So it will not affect the programs that you write in assembly language. So on this slide, there's one more question. Can one instruction set be realized using more than one microarchitecture? And the answer is yes. As I just explained, for the same instruction set, you can implement this particular processor using different microarchitectures. You may use one microarchitecture for the purpose of high performance, and you can redesign this chip using some very efficient power optimization techniques to reduce the power consumption of the chip, but still you maintain the same instruction set architecture. And that's still possible, and in fact that's very common in the industry. So hopefully these several points give you some idea about the views of these processors. Instruction set variety. For general computing, there are different kinds of instruction set architectures. You've probably heard of x86 and ARM. So those are two major instruction sets. And also AVR, the one that we use in Arduino. And there are many different instruction set architectures. So there are, the costs related to instruction set architecture specialization will be, for example, if you want to port any applications that written in assembly language, it's going to be almost impossible that you port the same program from one instruction set to another instruction set. Let's say you write a assembly language program for a x86 processor, and you want to run the same program on a ARM processor. You essentially have to rewrite the program. But that's the case only for assembly language programming. If you go up a higher programming language level, C or C++ or Java, the compilers for these programs, for these languages, handles a lot of the backend mapping from the syntax and semantics of the program to the machine's instruction set. So for those cases, for the high-level language programs, you don't have to worry about the challenges of porting from one platform to another platform. For the embedded computing domain, there are a variety of instruction set architectures. I mentioned a few ARM-based microprocessors and AVR-based microcontrollers, and also from the microchip, also they have the PIC microcontrollers. There's a lot of different embedded processors using different instruction set architectures. So in the embedded domain, the benefits of these different instruction sets are, generally for small programs, because for specific instruction set, they can be very compact. So to implement specific functions, you only need a few instructions. And from one instruction set to another instruction set, you may see difference in terms of the program size. And also depends on the registers that they have. Some operations may be efficient in one instruction set versus the other instruction set. So that's why you have a variety of instruction sets in the embedded domain, and you can choose those from, and you can consider together with the performance and power consumption of the processors to make a decision, which architecture you want to go with. Now here we just want to briefly compare different processor characteristics. For the general purpose computing domain, what do you want? And for the embedded computing domain, what do you want? What's the difference? You can come up with all kinds of answers to these questions. But in general, for the general purpose computing, you want your processor to be powerful, efficient in computing. You want the processor to be power efficient. But for general purpose computing, you will consider performance. You will weigh performance more than the power consumption. But it's always a balance whether how much you want to sacrifice on the power consumption to get higher performance. When you have a laptop, you have some general purpose processors in the laptop based on Intel's processors or AMD processors. You can get higher performance. You can have a processor that runs at 3.x gigahertz. Well, at least when the processor is put into the turbo mode, you will then have to consider, okay, if I run the processor at that high speed, what will be the power consumption? How much time my battery of the laptop can last? So that's always a trade-off there. For embedded computing, there are even more considerations. One is the power efficiency, because you tend to have embedded mobile devices, and you want this device to be powered by battery, so the energy efficiency is very important. You want that probably the most. And also you want this processor probably proficient in digital signal processing, if that's something that you do, maybe a DVD player or something. So that's the functionality that you will want to have to be able to run a specific task on this processor very efficiently. And also for embedded computing, you want to lower the cost. So the cheaper the processor, then that's more beneficial. So there are a lot of different characteristics of the processors in terms of performance, power, programmability, acceleration of certain tasks, and cost. So all these things that will becoming factors for you to make a decision. When we talk about microcontrollers, in our context, we specifically refer to those processors sometimes called as system on chip, or SoC. So these microcontrollers, they have a CPU core on the chip, and also it has a significant amount of memory for storing program and data, and some are volatile and some are non-volatile. And on this chip, you have a lot more components than a general purpose processor. For example, timers and I/O ports, or UART controller, or even USB controller on the same chip. So this is so-called system on a chip. So all the things you see here on the list, you don't have to have these components separately on the same PCB board. Instead, in a modern microcontrollers, you have everything on this list embedded in the same chip. So Well, so the question that showed up on the chat is Arduino Mega 2560 that we use is a microprocessor or a microcontroller. I would, say it's a microcontroller just because it has all these different components on the same chip. So we call it system on chip. In our context, we really call the microprocessors like those ARM-based or x86-based processors that are not specifically for embedded applications. But I have to say that the boundary between microprocessors and microcontrollers are getting blurry. People can say these two interchangeably, especially when they talk about microcontrollers. Some people say it's a microprocessor, but not the other way around. I would say the microcontroller is more leaning towards the embedded domain. So it's going to be a lot more components on the chip, even much simpler. For example, the CPU core will be simpler. The data width sometimes 8-bit or 16-bit. Some amount of memory, but with a lot of different components on the chip, timers, UART, USB, I/O ports. So when you see something like this, we call them microcontrollers. Okay, and microcontrollers typically for limited energy usage. So the power consumption, the low power is a desired feature. Also for these chips, they can put themselves into sleep mode. That will even lower the power consumption. And there are many different applications of microcontrollers or embedded microprocessors. Okay, in industry control, there are many situations you want to have a sequence of operations. So in a manufacturing pipeline, you may have different valve or different devices that you want to turn on and off in a sequence, and you will need to use these type of machinery or physical system to change the quantities of actuators, or based on the sensory input, you want to affect the process of the manufacturing pipeline or platform. So in these kind of situations, people can use so-called programmable logic controllers, or PLCs. PLCs is a unique categories of microcontroller system. They are used primarily for industrial automation. They are intended for continuous operation and also very hostile environment. For example, very high temperature or very low temperature, noisy, or strong magnetic interference. So these hostile environment can pose challenges to the other type of microcontroller or microprocessors, which are designed to operate in a pretty normal environment. So for PLCs, these type of controllers, they are programmed using so-called ladder logic. You often use a specific integrated design interface provided by the vendor. It's different from you writing some language code, but they are basically stitching up these different logics to form the control sequence. And so that you can use to define any actions on relays and switches. So for this class, we're not going to focus on PLC, so I will just give you such a short introduction. And if you're interested, you can get some reading online. But we mostly talk about embedded controllers, embedded processors. I'm going to talk about the signal processors or signal processing, digital signal processing processors first. And in the second half of this lecture, I will give you specific examples on the microcontrollers. So embedded signal processing is very common. It's used in cases for, process any signals, sound waves, magnetic waves, or images. And these embedded computers are very frequently used to control a process or otherwise to process signals. There are a lot of different signals coming from the physical world, and from the cyber perspective, we need to, of course, read these signals, feed them into the system, and then be able to process them. So as we show on the figure, in the figure on the right, that we have a physical plant. It's a physical world. It has a lot of sensors, actuators, and we will get the data from the sensors and apply them in a controller. So that's what we are designing using microcontrollers or DSPs. And using the output from the system, we will then control the physical process, maybe control the actuators or apply any actions. So in this process, we often use so-called filters. And we'll go through a few slides to give you an idea of what is a filter and why it's important, and especially how we can leverage processors to perform such operations as filters. So this is a circuit that you may have seen in your prior circuit theory class. This is a very simple passive low-pass filter. We have a resistor and connected to a capacitor in series. And we have an input signal, Vi, and we have an output signal, V out. So VO, that's the output. So what this circuit does is really to apply some processing, this so-called filtering, on the input signal, which assume it's a sinusoidal signal that will carry out different frequencies of signals. And this passive filter, low-pass filter, will be able to filter out the frequency band that beyond certain cutoff frequency. So this is the figure that try to characterize this circuit. What we're showing here is so-called frequency response. The frequency response figure shows that if we look at the amplitude that coming out of the circuit, compare that with the input signal. On the x-axis is the frequency that you may have on the signal, and the y is the amplitude related to the original input signal. What we see here, the general trend is that, as we said, this is a low-pass filter, so you expect that the amplitude will gradually decrease as the frequency increases. And at some point, in fact, for this particular circuit, if you calculate the cutoff frequency, it's about 1 kilohertz. It's 999 or 994, something like that. So this is the frequency we call it cutoff frequency. Here, beyond this point, the signal will be the output signal will be greatly dampened or reduced. So this is the result of this low-pass filter. Now, one thing we want to show is the step response. For step response is essentially when you have a voltage 0 as an input, and momentarily you apply that or change that to voltage of VDD. So how will the output respond? And because, as you know, that when we have such a sudden change, and the capacitor will go through a very dynamic process. At the very beginning, the voltage here is 0, and then it'll accumulate charges, and then the voltage will gradually increase. As a result, the difference between this input and output is going to be reduced gradually, and then as a result, the current going through on the circuit is reduced. So what we show here is essentially how the output respond when your input suddenly change from 0 to 1. And of course, you can see this is a very dynamic process. You can see as the time goes forward, the voltage on the output gradually reaches the same voltage as the input side. Another characteristic about this low-pass filter is the impulse response. Impulse response is a function that reflects the kind of the transfer characteristic of the circuit, in a sense that it estimates the distortions of this circuit for the signals passing through it. And this distortions, it's also related to time. And as we start, the distortion is going to go spike. As we go forward, it gradually goes down because the dynamic changes is not as significant as before. So this impulse response tries to capture the transfer effect of this circuit applied to the input signals. One takeaway message from this impulse response is that the actual output that you see on the output side is a transfer function that we applied to the input signal. So this is the transfer function will be applied to whatever signal that you apply on the input side. And the way we determine the actual output signal is to do a signal convolution process. So this convolution process will apply this impulse response function, which is determined by the filter itself. So this is the HT. And with the actual input signal, FT here. So this is the input signal. And this sign here, this is the convolution operation. And this essentially tells how we can determine the actual output based on the input signal and the time-dependent transfer function given by this filter. So this is the principle of operation of this low-pass filter. So what we saw earlier was what will happen if we have actually a circuit that built into our system to apply this filtering on the input signal. Now, I want to make it clear that what we want to do using a processor is to what we want to do using a processor is to basically, let me go back a little bit. Instead of using a analog circuitry, we want to use a processor to apply a similar operation on this input signal. As a result, we expect that the processor will give us roughly the same output voltage amplitude as if we have an analog circuitry. So that's the purpose of our digital signal processing, that we want to run this signal processing function using a processor. So in the next few slides, I'm going to explain how we can approximate this process and what's the implications on our processor design. So first of all, we need to sample the impulse response. So the impulse response is this curve that we saw earlier. We want to use the microprocessor to be able to capture this transfer function, which describes the filtering effect applied by this filter. One way we can do is we'll do some samples. As you can see, even we know that this original impulse response function is a continuous function. We here only sample a few points, and we chose to use this 250 microsecond as a sampling period. That gives us a sampling rate of 4 kilohertz. So we use these samples, and specifically we can see we have a few values that we will get from this curve. The first one is 6,250, and the second one is 1310, and then 275, and then 58, and then 12. So essentially we can do this sampling to get a few data points. When we sample, we get a few sample values. We can actually scale them to make the computation simpler, more efficient, because overall this is a linear process. We can later scale them back. So what we do here is we take the sample values and then we scale them down by 100 and then round the result to the nearest integer. Also, we need to sample the input signal because we are gonna use the convolution function to apply on the input signal. So we'll do the sampling, even though the input signal might be a continuous signal. And we'll use the sampling rate of the same as the impulse response. So for this case, it will be 4 kilohertz. Now here's a question, what's the requirement on the input signal? I'm asking about the input signal, specifically about the frequency of the input signal, because the sampling rate is at 2 kilohertz, and we should not have a input signal that's higher than 2 kilohertz, because we need to at least double of the frequency of the signal to be able to sample correctly without aliasing. Okay, then we can then apply this convolution function on both this input signal and impulse response. And what you see here, the first line of the formula is the convolution operation in the continuous domain. We have this integral operation to calculate that. And this f tau is the input signal at that tau moment, and h is the impulse response at the t minus tau moment. So we're talking about the past a few intervals. And then in discrete form, we will simplify the original formula with this the second line of the formula. Here, the capital N is the number of samples of the impulse responses. Essentially, we are looking at this point, when you have a input signal or the past N input signals, and with the corresponding impulse response samples, we can apply this multiplication and then do summation to calculate the output voltage. And then we can implement this using so-called the finite impulse response filter. And in this case, we chose capital N to be 4. That means we're going to use a 4-tab finite impulse response filter. You will see shortly what does 4-tab mean. But essentially, mathematically, you can see that we are using the past 4 samples to calculate the value of the output. This VI is the input, and H0, 1, 2, 3 are the sampled points values from the impulse response function. And this V, K minus 1, K minus 2, K minus 3 are the samples of the past before this current data point on the input. So we'll move forward by replacing the coefficient with the values that we sampled from the impulse response function, scaled down by 100. So we have 63, 13, 3, and 1, and we apply those numbers in this final calculation. So this is what we have as the filter structure. What we have here is several coefficient numbers that we sampled from the impulse response function. This here is actually a 1, but it's omitted because you multiply 1, that's the same thing. This sigma, first of all, this is this symbol here represents a multiplication operation, and this symbol represents a accumulation or addition function. And this delay is added to get the samples from the past. So as you can see that for the input signal, you will go through these several stages, multiply, accumulate, with delay, multiply, accumulate, and so on. And eventually we'll accumulate all the 4 terms and then get the output of the voltage. So if we do that, so we'll be able to plot the frequency response. If you recall, at the very beginning, we had a frequency response diagram that shows the original low-pass filter circuit. How does that apply to the input signals? When we compare these two, we see that the one we used with microprocessors has similar trend. However, it does not follow exactly what we have seen on the analog design. Well, you can expect this is probably going to happen because we did a lot of assumption or simplification when we process the signal. First of all, we only use 4 samples of the impulse response, whereas the original circuitry, that impulse response function, is a continuous function. But for our design, we use 4 samples, which makes the FR filter it's very simple with only 4 tabs. And as a result, that degrades the filter performance. So our first step is that we use approach using digital processors to apply filtering on any signals, try to emulate the original analog design. Even though this does not, match exactly the analog circuitry, but we may be able to improve this performance by using different designs. We may use more samples. That's one way to do it. And in that case, the filter will be using a different number of coefficients. And also we can we can increase the number of tabs so that instead of 4, we can have a lot more of these multiplication operators with more coefficient and accumulators, so that we can get much closer to what we have in an analog circuit. So in this design, we essentially have 2 major operations: multiply, that's multiply with these coefficients, and then accumulate, so that's for every single stage. So for multiply, we need a very fast integer operator. And also for accumulation, we need large integer adders and accumulations, because the eventual value could be pretty big. And we would like to have both for our design. And that's exactly what we have in the digital signal processors, or DSPs, where we have the so-called multiply accumulation operators. So DSP, digital signal processors, provides fast and efficient multiply accumulation instruction. And typically it's included a relatively large accumulator to accommodate the multiplication result. Also, they use Harvard memory access architecture, which I'll explain later. Harvard architecture really means that you have separate program memory and data memory. And they also provide ways to automatically increment addressing mode addresses, so you can quickly get to the next sample without having to specifically increment the pointers to access data in memory. They may also support circular buffer. That's going to be efficient implementation of the delay lines. And also they may support zero overhead loops when you have such large number of loops to operate on these samples. Okay, so what we explained earlier was the filter design using digital processors, so that we don't have to have a analog circuitry. We can use a microcontroller to perform the same operation. That will give us a lot more programmability. We can choose different sample coefficients. We can apply to different input signals to emulate different designs of filters, not only low pass filters, but in some cases high pass filters and so on. All right, so that was a discussion about digital signal processors. In the next few slides, I want to briefly talk about parallelism and concurrency. Parallelism and concurrency are important concepts related to multiple tasks being executed. Embedded computing applications typically do more than one thing at a time, because the complexity of the cyber physical system, by nature, there are a lot of things happening at the same time, and you will desire your physical, your cyber systems will be able to support, the computation of different tasks. But I want to differentiate 2 concepts. One is concurrent, one is parallel. You may see these 2 concepts, 2 terms in different textbooks and papers. They refer to different things, even they are quite similar. Both of them are talking about multiple tasks. But when we say concurrent, we are talking about when tasks are conceptually executed simultaneously. You can think about it as a kind of a logical, per se. If two tasks both are being both started but they have not finished, you can call them concurrent. But when this concurrent, doesn't mean that they are being executed at the exact same time. At the instruction level, they may execute one after another, maybe take turns. They don't have to be executed exactly the same time. And that's when we call them concurrent. In contrast, when tasks are said to be parallel, they are physically executed at the same time. Which means that from the hardware perspective, from the processor perspective, you have to have more than one processor cores in order to execute more than one task at the same time. And that's not the case for concurrent or concurrency. So when we say parallel, we really mean that for these multiple tasks, they have to be executed on different processors at the same time. Whereas the concurrent concept is not very strict. It just means that processes are in progress. They both of them or all of them have not finished it. They can proceed at the same time. Okay, about the taking advantages of this parallelism in applications or the hardware architectures to improve performance, that's a big topic. What we want to discuss here is just give you some idea, what can we expect when we have parallelism in the application or multiple cores that in the processor that you can use. Various current architectures seeks to improve performance by finding and exploiting potentials of parallel execution. If you find there are two parts of your program that can be executed at the same time, and you have resources, for example, you have 2 cores or more cores in a processor, then you have a chance to improve the performance. And with multiple processors, you often improve the processing throughput. Let's say you have a digital camera, let's say, and you are going to take continuous shots for certain sports scenes. So you can hold the shutter, and then the camera will start firing up and taking pictures continuously until you release the shutter button. So some cameras, they say, okay, they can do continuous taking pictures for 10 pictures per second or 15 pictures per second, which is pretty fast. But we're really talking about the throughput in a sense that you can expect that you can take this 15 pictures in 1 second, but that does not translate that you will it takes one second or half second to finish the processing of one single picture. So the throughput and latency are not always the same. If you have multiple cores, you have multiple processing units, you can improve the processing throughput because essentially you can assign different tasks on separate processors. But it does not always mean that you will take shorter time to finish processing one picture. So that's one thing I want to just clarify when we talk about this parallel execution. one other point is that many embedded applications rely on results being produced at predictable regular rates. So the result must be available at the right time. This is especially true for real-time systems. When we define real-time system, we're saying that if you get this input signal, you have to finish processing within 500 milliseconds. So that's one example how you define this constraint. There are hard real-time systems and soft real-time systems. Hard real-time systems are where you have to follow exactly the schedule. You have to get your input signal within this first 250 milliseconds, process it in the next 500 milliseconds, and then apply control on the actuators in the next 100 milliseconds. And next round goes the same. And that's a good example of hard real time. So everything has to be timed precisely, and your system will go on like that. If there's any violation of these timing constraints, then the system is going to be reporting a serious error or shutdown, or do some drastic last resort to tolerate this, to protect from any serious consequences. On the other hand, you can have soft real-time systems. So even though you may have such timing constraints on different tasks, but if things don't go exactly as the schedule, it's probably fine. You can just put that into the log, saying this the thing happened, and your system can go on. So timing is really important for many of the embedded systems. Some hard real-time system, timing is kind of the lifeline. If timing violation occurs, then the system is gonna crash. But some other cases may not be the same. Parallelism, we have temporal parallelism, or pipelining. So you can, apply. You can run the task in different stages, and in different stages you can, in different stages of the pipeline, you apply operations on one piece of data, and then the other pipeline stage you will do something else. So that goes along the time axis. Spatial parallelism really is about how you can execute multiple instructions at the same time, using either multi-core or very long instruction word, where you can embed different instructions in this long word, or superscalar machines, processors that you will schedule multiple instructions so they can be on the fly, being executed before any of them committed or finished. So those are more related to some design options for microprocessors and microcontrollers.